So here comes, this is section 3.1 homework. I'm going to do just a few of these. So you guys worked on number 45. Let's talk about it. And the directions are just find the derivative. Okay? So, of course, in the old day, you'd have to do the limit as h goes to 0. Now we say we have some shortcut rules that I hope are going to help. So it says f of x equals the cube root of x squared. And you can't see any of that, can you? So let me pause, or else we're not going to do anything. Television audience at home can see. Okay, so f of x is the cube root of x squared minus 4 over the square root of x, and I'm supposed to find the derivative. And a lot of times when you have to find the derivative, first step is going to be, let's rewrite the function. Because the way it's written right now, it's hard for me to really work with. I'm going to rewrite it using exponents. And so the first one I'm going to rewrite, do you guys know how? X to the 2/3. That might not be fresh in everyone's memory, so let me give you a little rule that kind of helps. If you have x to the p over q power, where that's some fraction, p is the power, and q is the root. Okay? What I mean by that is, since this is cube root, we put a 3 in the denominator, right? So over here, you could write minus 4 over x to what power? What do you do for square root? Do you guys know? 1/2 power, right? But there's a better way to write this than what I just did. I'm going to write it as f of x equals x to the 2/3 minus, do you know what I'm going to write? 4x to what power? Negative 1/2, because what does the minus sign tell me? Yeah, it's basically saying take the reciprocal, so if it's in the numerator, it goes to the denominator. If it were in the denominator, it would go to the numerator. Okay? So now I've done rewriting. Now I'm ready to compute the derivative. So the derivative, f prime of x, well, you guys know the rule, right? What's the rule? Right? What's the rule? Bing, bing? Well, really, the rule is bing, bing, bong. But that's Monday. Okay, so Monday, we'll learn the full rule. But so far, all the problems I've done, bing, bing, we've gotten away with. So how does it work? Bing, what do I write down? Bing. And then I'm going to write x to the negative 1/3, because I subtract 1 from 2/3, and so it becomes negative 1/3. Minus, and by the way, that 4 is a constant, so you can kind of ignore it. Just write it down. And now I'm taking the derivative of this x to the negative 1/2. So you know what I'm going to write down next? Almost. Bing, negative 1/2. And then bing, we write x to the what? Yeah, you better be good with your fractions in this class, huh? I mean, we have to be careful, right? There's a lot going on here. So that's actually an answer. I don't think it's the answer they had in the back of the book. I'm guessing they simplified it. So what I would probably do next is write this. I would write f prime of x equals, this is 2 over 3 times the cube root of x. Does that make sense to you guys? Cube root because it was 1/3 power, and then why is it in the denominator? Well, that's because it was a negative exponent. And then I'm going to put plus, and then I think I would just write 2, maybe over x to the 3/2 power. Or maybe you could write, oh yeah, why is it plus? Because there was a minus minus. Maybe they put this as their answer. 2 over 3 cube root of x plus 2 over maybe the square root of x cubed. Something like that might be the answer. Okay? That's another way to write it. Lauren, does that help? Okay. So we took care of 45. Now the next question that you guys asked me about was 65. I'm going to go ahead and look at that one with you. They say write the domain, use the addition rule, compute f prime using the rules from this section. So people were okay with the domain, but they just had trouble with the derivative. So let me go ahead and try 65 part C. So let's see. Oh, no, I'm wrong. 65 is the next section. It says write an equation of the tangent. All right, well, I'm going to have to go through the whole thing, I think, to do this. They want a couple of things. So, all right, let's work on 65. It says, although the funny thing is 65 and 69 are so similar. You know, I think if I do 69, whoever asked me for 65 will be able to do it. So let me try 69. And then you tell me if you have another question on 65. Let's wait on that. 69. F of x equals x to the 2/3. This one's just a little more complicated, so I'd rather start with this. And it says at x equals 8. By the way, do you know what the graph of x to the 2/3 looks like? That's what I thought you'd say. That's why I decided to do this one. Do you guys know what the graph of x cubed looks like? A couple of you are hinting that you might know. Okay. Of course, I can always check on the calculator these things, right? So I'm going to do that. I'm going to go to the calculator. I'm going to... Oh, that's not what it looks like. That's supposed to trigonometry. Okay. Good stuff. Well, let's go to here. We were graphing y equals x. There's the caret key. That's what you want for exponents. So, for example, x cubed. I said I was going to do that. Graph. How many have seen that curve before that's on your screen? You've seen x cubed. I don't know if you'll remember x to the 2/3, so that's why I thought we'd do that one instead. When I'm going to graph that one, you need some parentheses here. Open parentheses. Because remember, it's going to do exponents before dividing unless you have parentheses. So there's x to the 2/3 power. Let me graph that one. And by the way, let me hit the standard zoom, choice 6. Okay. Ooh, look at that. So that's an interesting curve, and I want to talk a little bit about that today. Okay? But that's my picture. Y equals x to the 2/3 would look like that. Okay? So, if we're going to find the derivative, which is the first thing they say, part A, you guys get f prime of x equals bing, bing, 2/3 x to the negative 1/3. Right? How can I rewrite that? 2 over 3, what am I going to say next? What are you going to say? Cube root of x. By the way, you notice I can take the cube root of almost anything, right? You can't take the square root of everything, right? Because what happens if you take the square root of a negative? Right? We can't. It's imaginary. We say keep it real. Can you take the square root of negative 8? Square root? No, but cube root? Cube root of negative 8? Cube root of negative 8 is negative 2, right? So we can do that. So you'll notice that, you know, when I look at my xy chart, here's the y equals x to the 2/3. I'm taking a cube root and then I'm squaring it, right? When I look at the table, let's say, if I hit second graph, you can do that. You can plug in positive numbers, you can plug in 0, you can plug in negative numbers and compute the values. Okay? But we're going to see that the derivative doesn't necessarily work everywhere. Now, I guess what I care about is, does the derivative work when x equals 8? Because that's what they're interested in. So part B says, find the slope of the tangent line. Here, let me try and sketch the graph of f. So I know that 0 to the 2/3 is 0. And I know that 1 to the 2/3 is 1. And I also know that -1 to the 2/3 is 1. Maybe to see that, you do this. So that's the cube root of -1 squared. So it's -1 squared, so it's 1. I mean, you could work this out if you want. But basically, the picture looks kind of like this. So by the time I get to x equals 8, I'm out here somewhere. And what part B asks is, let's find the slope of that line. Well, how do I do it? I do f prime of 8. So I'm going to use that little formula that I just came up with. 2 divided by 3 times the, what is the cube root of 8? So it's 2 divided by 3 times 2. So it's 2/6, or 1/3. That's the slope of the red line. Okay? So that would take care of 69B, which you asked about. And the person that asked about 65 asked about part C. For part C, we want to use point-slope form to come up with the equation of the line. If I want this green line, I'm going to use y minus y1 equals m times x minus x1. And now I know what I can do. I can fill in the 1/3 as my slope. I guess the only question is, do you guys know what to put in for x1 and y1? I know what to put in for x1. What would you put, Matt? 8. Put your 8. They gave me 8. What about y1?
You have to plug it into the original function to get the y value.
Okay. So we're going to do 8 to the 2/3 power. And that can be an issue. Do you guys know? I showed you how to do -1 to the 2/3 power. Let me try computing f of 8. It's 8 to the 2/3 power. You guys have a choice. You could either do the power first or the root first. I like doing the root first. Because what's the cube root of 8? 2. And then square that, you get 4. So I would say that my equation would be something like that. What if you want to graph it? That's what part D said. Well, I guess I could solve for y. I'm not going to multiply this all out right now because I don't really care to. I'm just going to add 4 to the other side. I'm going to type that into the graphing calculator. Because, you know, I may as well let the calculator do the work for me. So it says we're going to do 1/3, so that's 1 divided by 3, times, open parentheses. Let's see, I have x minus 8, close parentheses, plus 4. Right? I want to go ahead and graph that. There's my line. Is it tangent right there at 8? Sure looks like it, right? I mean, one thing you could do is you could say, hey, where do these things intersect? So if I hit second, calculate, choice 5 is how you get intersection. First curve is the curve, second curve is the line. Do I have a guess? Well, yeah, they intersect a couple places, so I'm going to move over here to the right so that it knows, I really want to know where do they intersect over here. Enter. See if it finds it. Oh, it didn't. It found -1, 1. That's interesting. It didn't quite find where the intersection was over here. That's because it's a tangent line. So, well, we're able to get a picture. More about it. You guys look at this function. x to the 2/3 power. Is it true that you could put any value in for x you want in the original function? Even negative numbers, right? We said that's fine. What about 0? What's the cube root of 0? Cube root of 0 is 0. If you square 0, you get 0. That's all okay. But look at the derivative. The derivative right here, guys. Is there anything you would not be allowed to put into that function? Why not? Because, yeah, it's undefined, right? We know you can't divide by 0. So we would say that this function, the original function, is not differentiable. There's the word. At x equals 0. And you can actually see that. Because if you look at the function, now that picture is a little confusing because I graphed the tangent line, so I'm going to turn off the tangent line. Just by not highlighting it, it won't graph it. So I'm going to go ahead and just graph the function. You guys see that? There's a feature to this graph. When it comes down, see how it almost looks like my daughter when she draws like a bird in the sky near the horizon, right? You have this little pointy part, that's called a cusp. And if you have a cusp, it's hard to really say what the slope would be there. I mean, these slopes are all going down, but then that would be like a vertical line. You see that? Anytime we have a cusp, that's a situation where it's not differentiable. And I was talking about this a little bit, actually, right when we started Chapter 2. Let me go back to it. Let me show you this slide. Well, I skipped that one. I'm going to do that in a second. But remember me talking about good example functions, okay? Do you remember what that first symbol stands for? No. It's, yeah, rounding down. It's called the greatest integer function. See, that was an example of a function that is not continuous. Now that next function, do you know what those bars mean? I bet you do. Those mean absolute value, okay? Absolute value function. And by the way, I guess it might be good for me to use that as an example. Oh, the last example, notice I'm doing cube root. That's kind of like what I just did, so I'm going to skip that. But I'd like to talk about absolute value for just a second with you. Matter of fact, let me make it even easier. Let me just talk about f of x is the absolute value of x. Do you guys know what the graph of that function looks like? Well, some of you do from college algebra, I see. Because, like, if you take the absolute value of 2, what's that? Or the absolute value of 1, or the absolute value of 0 is 0. But what's the absolute value of negative 1? What's the absolute value of negative 2? So you really do get, yeah, it is similar. It's a v, right? Okay? We would say that this function is continuous at x equals 0. Continuous. But it is not, however, and the word is differentiable at x equals 0. Okay? And by the way, I gave you a definition of continuous. I'm going to remind you of it. When I say it's continuous at x equals 0, what that means is the limit as x approaches 0 of the absolute value of x equals the absolute value of 0. Right? The limit as x approaches c of f of x equals f of c. That was the definition. By the way, what's the absolute value of 0? Okay, you know that. Would you agree that the limit exists? Remember, for the limit exists, we had to talk about the right-hand limit and the left-hand limit. From both sides, are we getting closer and closer to 0? Yeah, so it's continuous. You could pick it up you could draw without picking up your pencil. But it is not differentiable. Anyways, that homework problem you asked about reminded me of this example of a function. And again, I wanted to make that point because we have a theorem that I think is important. It says, if f is differentiable, then f is continuous. But I said the converse is not true. Do you guys know what I mean by the converse? What would that mean? Yeah. It might not be differentiable, right? I just showed you that example. Absolute value is continuous, but where is it not differentiable? Where is absolute value not differentiable? Right at 0. Why? Because what's that called? That's called a cusp. Right? So what would be the slope of the tangent line? Would it be positive? Would it be negative? I don't know. You can't draw a single unique tangent line at a cusp. You guys with me? But it's like a house. When you build a house, differentiability is like the second floor. First you have to be continuous. If you have a function that's not continuous, forget taking the derivative. Okay? Well, this one's continuous but not differentiable. Guys follow? Okay. I want to make sure I made that clear.